Human-Machine Interface HMI Tutorial Part 6. Graphic Display Configuration Guidelines. A coherent, readable, and consistently structured graphical interface is essential for effective operator performance. While graphics are a powerful tool for situational awareness, poor design through clutter, disorganization, or inconsistent layouts can hinder navigation, increase error rates, and cause delays in decision-making. To avoid this, display design must be guided by ergonomic and information hierarchy principles. The following sections provide best practice recommendations for the density, structure, and layout of process scheme graphics. Density of information on screens. An operator display must strike the right balance between providing sufficient information and avoiding visual overload. Overcrowded graphics lead to longer search times, reduce clarity, and increase cognitive load. As a general rule, no more than 40 live data points should be shown on a single screen. Live data points include real-time process values, controller outputs, alarms, and trends. Exceeding this limit can overwhelm the operator, especially under stress or during an abnormal situation. To maintain effectiveness, data shown on a screen must be task relevant. Each display should present only the data required to understand the current state and perform the necessary action. Where more information is required, it should be layered through navigation, such as drilling down into detailed views or calling up supporting windows. Supporting information can also be toggled on or off to reduce visual complexity. For example, signal lines or tag numbers may be hidden by default and revealed on demand. Summary indicators or bar graphs should be used where possible to condense information into interpretable visual cues. For complex equipment or process areas, information should be split across multiple logically linked displays rather than crowded into a single schematic. Generic graphic template. Consistency across displays is critical for operator orientation and rapid navigation. A generic graphic template defines standard zones and behaviors across all process graphics, ensuring uniform placement of navigation tools, faceplate targets, and titles. This uniformity allows operators to instinctively know where to look and how to interact with any display, regardless of the unit or function. Each display should follow a structured layout, including graphic title area, reserved for the display name and equipment identifiers, typically in the upper left corner. This helps the operator confirm they are viewing the correct screen. Navigation targets, placed consistently along the edges or corners of the display. These provide quick access to related views such as control groups, trend displays, tag details, or help windows. Command zones, dedicated sections, usually near the bottom or right-hand side for control interfaces, faceplate activation, or soft key entry. These zones may be used to display controller faceplates, mode settings, or toggled control states. Process graphic area, the central region where the schematic and live data are displayed. This is where equipment, piping, process values, and control elements appear. The graphic flow should reflect natural reading behavior, left to right, top to bottom. This helps the operator mentally follow process direction and logically interpret the flow of information. Screen regions should be clearly differentiated and overlapping interface elements avoided. A site-wide graphic template should be agreed upon during the HMI configuration phase, and all process displays must conform to this standard. This also applies to third-party packages integrated into the DCS. Visual consistency must be maintained regardless of the underlying source system. Layout for process scheme displays. The layout of process schematics should mirror the logical process flow and emphasize clarity. Diagrams must be based on major equipment, e.g. vessels, columns, compressors, and task-driven control schemes. Operators should be able to understand not only what is happening, but also where and why. Every graphic should support a clear control goal, whether it's balancing a furnace, managing a distillation tower, or isolating a pump for maintenance. Graphics should generally be oriented left to right, with process streams and control signals entering from the left and exiting to the right. This directional logic mirrors the reading flow and simplifies process comprehension. Vertical scrolling should be avoided wherever possible. Horizontal flow is easier for operators to interpret quickly. Process lines and signal lines must be laid out clearly with minimal crossing or overlapping. Unnecessary complexity, such as excessive piping or instrumentation that does not serve an operational purpose, should be omitted. Elements such as manual isolation valves or bypass lines should only be included if they are critical to the task being supported. Visual noise should be minimized. Each schematic must be purpose-driven. For example, a furnace control graphic should include all combustion, fuel flow, and coil balancing information, but exclude unrelated downstream data. This task-focused design ensures that each display provides only what the operator needs to perform specific actions or solve a defined problem. Attention must also be given to the physical limitations of the viewing hardware. The outer edges of the display may be obscured by screen bezels or poor viewing angles. Therefore, no critical data or control elements should be positioned too close to the screen edges. Display testing with actual hardware configurations is recommended to validate visual accessibility. Summary. Effective display design requires more than technical accuracy. It demands attention to ergonomics, cognitive load, and task relevance. Limiting data density improves focus. Standard templates ensure intuitive use. And logical layout of process schemes reinforces operator comprehension. By following these principles, HMI graphics can support fast decision-making, reduce operator fatigue, and improve both safety and operational efficiency across the plant. Human-Machine Interface HMI Tutorial Part 7. Configuration Standards. Establishing and enforcing consistent configuration standards is vital to the success of any HMI system. These standards serve as a visual and functional language that operators quickly learn to interpret, allowing them to react to changing plant conditions without hesitation or confusion. Standardization ensures that displays are intuitive, alarms are clearly distinguishable, process conditions are instantly recognizable, and graphical symbols convey meaning without requiring reference documentation. This section outlines the key configuration standards for color usage, highlighting, symbols, data presentation, and other display elements. Color conventions. Color is a powerful tool when used correctly. It draws attention, conveys status, and helps differentiate elements. However, excessive or inconsistent use of color can lead to confusion and eye fatigue. A disciplined color scheme must be adopted, with specific colors reserved for key functions. Foreground colors used for data, equipment states, alarms include red, yellow, green, cyan, magenta, and white. Backgrounds should be neutral, typically light or dark gray, to reduce glare and visual distraction. Common color usage guidelines include red, high priority alarms, equipment in trip or fault condition, IPF activation. Yellow, medium priority alarms, cautionary states. Green, normal or healthy status, e.g. valve open, motor running. Magenta, faulty or unreliable data, bad signal status. Cyan, used in trend lines for process differentiation. White, standard process elements, normal data display, neutral text. Color alone must never be the only indicator of state. Redundancy is essential. Use color together with shape, animation, labels, or brightness to reinforce meaning. For example, an alarm could be red and blinking, while a bad value may be magenta with a label prefix U for unavailable. Avoid problematic combinations like pure red and blue, which can cause visual distortion, chromastereopsis, and avoid using blue for high-precision text or lines on dark backgrounds. Highlighting methods. Highlighting draws the operator's attention to critical or active elements. To preserve its impact, it must be used sparingly and consistently. Key methods include blinking, brightness variation, inverse video, and color change. Blinking, reserved for unacknowledged alarms or urgent operator prompts. Blinking should alternate between two intensity levels, not simply flashing on-off, and must cease once acknowledged. Brightness, used to emphasize selected items or active states within a group, e.g. a selected line path. Inverse video, commonly used to denote selected fields or manual data entry. It reverses the background and foreground contrast, making the item stand out. Color changes. As noted, these reinforce alarm levels or equipment status. For example, a pump icon may change from hollow, off, to filled green, running, to flashing red, tripped. Highlighting should always support a specific task, helping the operator notice what's changed, what needs attention, or what is active. Symbol usage and conventions. Symbols represent process equipment and must be easily understood at a glance. Standardized libraries should be developed using international conventions, e.g. ISA, PFS. Symbols should be clearly differentiated and reflect the physical arrangement and function of equipment. Arrows indicate flow direction. Shading or fill indicates status. For examples, open equals filled, closed equals hollow, transitioning equals inverse video. Pumps, running equals filled, off equals hollow, tripped, blinking red, fault equals magenta border. Motors follow the same visual behavior as pumps. Manual switches, static shapes unless shown for specific operations. Bad values displayed in magenta with coded prefixes. F equals fault, L equals last value, U equals unavailable. Symbols should maintain a minimum height of 5 to 6 millimeters for visibility from a distance. Labels, e.g. P101A, must be consistently placed, preferably below or adjacent to the symbol, and should never be vertically oriented. Line and equipment rendering. Process and instrumentation lines must be visually distinct. Main process lines, bold, e.g. 3 dot width. Utility or secondary lines, medium, e.g. 2 dot. Equipment outlines, thick and prominent, e.g. 4 dot. Instrument signal lines, dashed white, 1 dot, optionally toggled on-off using a touch target. Vertical line breaks at intersections help clarify crossovers. Avoid routing lines diagonally unless functionally necessary. Use consistent spacing to maintain clarity in densely connected areas. Process data representation. Numeric data must be right justified and formatted for quick readability. Units should be standardized and clearly labeled. Common conventions include flow, 4 digits with decimal, e.g. 1223.4 T for threshold. Pressure, 3 to 4 digits, e.g. 1.23 bar. Temperature, 4 digits with 1 decimal, e.g. 450.0 degrees Celsius. Level, percent values, e.g. 98%. Tank level, raw millimeter value, e.g. 1,500 millimeters. Data point behavior should be consistent. Normal, green text. Alarm, black text on red or yellow background, blinking until acknowledged. Manual entry, inverse video, white background, black text. Bad value, prefix plus inverse video, magenta with F for fault. Short duration trends, 10 to 15 min, may replace numeric values in subunit or unit displays to provide process history. These are particularly useful during shift changes or transient analysis. Bar graphs and radar charts. Bar graphs are effective for comparing values across multiple parameters or locations, such as temperature profiles across a column or multiple feed flows. They should be compact, aligned, and color-coded by parameter type. Radar charts, or spider diagrams, represent multidimensional parameter groups showing balance or deviation at a glance. These are useful for evaluating coil temperature uniformity, controller health, or energy balance. Windows and pop-ups. Dynamic windows allow temporary access to detail without changing the base display. Standard windows include alarm window, recent alarm list, faceplate for tag adjustment, trend window, small-scale trend chart. Help window, contextual instructions or warnings. Up to 4 windows should be allowed open per screen. A tiled layout is preferred over overlapping to maintain clarity. Window positions should follow a policy. For example, faceplates in the lower right, trends in the upper left, ensuring predictable display behavior. Summary. Configuration standards transform the HMI from a visual display into a high-performance operational tool. By carefully defining how colors, symbols, data, and layouts are used, the interface becomes consistent, legible, and inherently informative. Operators no longer need to interpret displays, they read them intuitively. With these standards in place, the HMI becomes safer, faster, and more effective. An intelligent interface that truly connects human decision makers with the complexity of the process they control. Human-Machine Interface HMI Tutorial Part 8. Alarm management is a core function of the Human-Machine Interface HMI, playing a vital role in safeguarding plant integrity, preventing process excursions, and supporting timely operator intervention. A well-designed alarm system is not simply a list of conditions that generate sounds or flashing lights. It is an engineered communication layer that filters, prioritizes, and presents critical deviations with precision. Poor alarm configuration leads to overload, desensitization, and increased risk of human error. Effective alarm management must therefore follow a structured philosophy, supported by technical implementation within the DCS. Alarm philosophy. A formal alarm philosophy defines the purpose, usage, and configuration rules for alarms across the plant. It establishes clear distinctions between alarms and messages. Alarms demand action, messages convey status or guidance. The philosophy outlines how alarms should be prioritized, displayed, acknowledged, and suppressed based on the severity of deviation, urgency of response, and potential consequence. Alarms should only be configured when the condition indicates a meaningful deviation from normal operation. Operator intervention is possible and necessary to avoid a trip or safety issue. The condition is not already managed by automated protective systems, e.g., IPFs. The philosophy must address nuisance alarm reduction, define when masking or grouping is appropriate, and specify standard rules for alarm colors, blinking behavior, audible tones, and message formatting. Alarms must support safe, timely operator decisions, not distract or overwhelm. Approach to alarm handling. Alarm handling follows a lifecycle approach: analysis, configuration, presentation, response, and review. The process starts with a multidisciplinary team defining the purpose and expected operator action for each alarm. Alarm conditions are then classified, prioritized, and configured in the DCS with corresponding logic, deadbands, and display behaviors. During runtime, the alarm system must detect conditions based on configured logic, e.g., HH, LL, deviation, rate of change. Filter transients using deadbands or signal smoothing. Assign priority and escalate as needed. Display the alarm in summary, faceplate, and graphic views. Support operator acknowledgement and logging. After the alarm event, logs and summaries allow review and continuous improvement. The alarm strategy must adapt to changing process conditions, updates to plant configuration, and lessons from operational experience. Multidisciplinary team analysis. Alarm rationalization is a collaborative effort involving operations, engineering, instrumentation, process safety, and control systems specialists. The team must evaluate each alarm in terms of purpose, what condition is being monitored; consequence, what happens if the operator does not act; urgency, how fast must the response be; mode relevance, is the alarm valid in all operating modes, e.g. startup, shutdown, regen? Operators contribute practical insight into usability and workload. Process engineers identify the impact of the deviation. Instrument engineers validate configuration feasibility and signal behavior. The team documents findings using an alarm classification sheet, which assigns a final priority based on consequence and required response time. Alarm prioritization and classification. Alarms are typically classified into 3 priority levels: high priority continuous tone, immediate response required, typically tied to process safety, environmental limits, or equipment trips; medium priority, yellow, intermittent tone, action required within minutes to avoid loss of control or economic penalties; low priority, visual only, informational or early warning, may not require immediate response. Each alarm should also be classified by operating mode applicability. Alarms that are only relevant during specific transients or unit modes should be suppressed or adjusted dynamically to avoid false positives. Typical urgency consequence matrix: major consequence, fast response, high priority; minor consequence, slow response, medium or low; no operator action possible, alarm not justified. Alarm configuration features. Modern DCS platforms offer a range of tools to implement alarm strategies. Alarm detection logic, configured at control block level, includes range checks, deviation alarms, and trip logic. Alarm deadband prevents chattering by requiring a defined margin before retriggering. Signal filtering smooths noisy inputs, avoiding false alarms from minor fluctuations. Alarm masking temporarily disables alarms during maintenance, transitions, or equipment downtime. Alarm grouping aggregates multiple related alarms into a single common alarm to prevent flooding. Auto acknowledge, used for expected alarms following certain trips or sequences. Active suppression, automatic disabling of known consequential alarms following a primary event. Static suppression, manual or operator-triggered masking of alarms during known conditions. Alarm presentation, configured through HMI color, blink, banner, audible tone, and window targets. Graphical alarm display configuration. Alarm information must be easily located, clearly understood, and visually consistent across all screens. This includes alarm summary view, lists all active alarms in order of occurrence with acknowledgement status and priority color. Alarm overview display, matrix or schematic view showing alarm status per unit or area, useful for high-level triage. Graphic integration, process items in alarm should change color, e.g., red or yellow, blink until acknowledged, and be selectable to view details. Faceplate indicators, alarm icons or text embedded within tag faceplates for immediate reference. Banner alerts, optional top screen message bars showing the latest unacknowledged alarms. Dedicated pages may also be created to show alarm suppression states, representative alarms, or dynamic alarm behavior per plant area. Audible alarm signals. The DCS should emit distinct tones to differentiate alarm levels. High priority, continuous high-pitched tone. Medium-low priority, intermittent tone. System alarms, e.g., communication faults, separate tone, distinguishable from process alarms. Volume must be adjustable but clearly audible above control room background noise. Tones should cease once alarms are acknowledged or cleared. Alarm behavior by plant condition. Different plant operating states require different alarm handling techniques. Shut. Steady state, alarm grouping, suppression of inactive systems. Upset conditions, active suppression of expected secondary alarms, prevent overload. Startup, shutdown, dynamic alarm settings and masking of irrelevant alerts. Plant stopped, static suppression of alarms from equipment known to be offline. These behaviors must be embedded in DCS sequences or logic blocks, governed by operating modes and permissives. Summary: alarm management is not just a technical function. It is a vital layer of operational decision-making and process safety. Through structured philosophy, multidisciplinary analysis, and intelligent configuration, alarms can guide operators rather than distract them. The goal is to deliver timely, actionable, and relevant alerts in a way that supports calm, confident control room operation, even during plant upsets. A properly managed alarm system turns noise into insight and transforms the HMI into a true partner in operational excellence. Human-Machine Interface HMI Tutorial Part 9. Console Design. The control room console is the physical embodiment of the HMI. It is where information, action, and decision-making converge. A well-designed console layout ensures that operators interact with the process safely, comfortably, and efficiently. Console ergonomics, component arrangement, screen visibility, access to critical functions, and human factors design all have a direct impact on plant operability and incident prevention. The goal is to create a working environment that minimizes fatigue, supports task flow, and ensures effective monitoring and control throughout every operating condition. Operator interface layout. The layout of consoles within the control room should reflect the functional and process logic of the plant. This means aligning console positions with process flow, either left to right or right to left, based on local conventions and operator preference. Process sections that interact frequently or require joint decision-making should have consoles arranged close to one another, ideally forming a U-shape or C-shape to support operator communication and collaboration. Console layouts must also consider future expansion, allowing additional workstations or equipment to be added without major redesign. Link analysis tools should be used during design to determine how operators move between systems, communicate, and access information. This ensures that console grouping supports workflow rather than obstructs it. Each console must have an unambiguous process boundary, defined sets of units or functions under its control, so operators clearly understand their responsibility area. Transition points between console responsibilities should be visible and traceable across displays. HMI console types. Two main types of console configurations are used: freestanding console. Equipment, VDUs, keyboards, pointing devices, is fixed into an enclosed cabinet structure. These offer a traditional appearance but can be less flexible in layout and hardware changes. Desktop or workstation console. Displays and peripherals are placed on open desks. This configuration offers greater adaptability, easier maintenance, and is often more cost-effective. Regardless of type, console furniture must meet ergonomic requirements. Work surface height, leg clearance, screen visibility, and reach distances must accommodate a range of user sizes, typically from 5th to 95th percentile. Adjustable furniture or peripherals, swivel displays, sliding keyboards enhance operator comfort and posture, reducing fatigue over long shifts. Displays and controls must be within comfortable reach without the need to stretch or rotate significantly. No controls should be positioned above shoulder height for the smallest expected user, and no critical displays should be located where they would require head tilt or awkward eye tracking. Number and role of consoles. For a typical set of continuous process units with 200 to 400 control valves, a standard configuration includes main console, 4 VDUs, dual keyboards and pointing devices, communication and CCTV panels, and a hardwired switch panel. This is the operator's primary interface for monitoring and control. Secondary console, 2 VDUs with 1 keyboard and pointer, used during plant startups, emergencies, or operational peaks. This may be shared between units. Supervisory console, a single VDU with keyboard and pointer, often located in an adjacent office, used by operations managers, engineers, or technologists for read-only monitoring. With authorization, this can be temporarily switched to read-write for tuning or system maintenance. Additional consoles may be placed remotely for simple or standalone units such as water treatment systems or product blending facilities. During plant upsets or emergencies, a single operator should not be responsible for more than 3 active screens at once, e.g., an overview display, a detailed process graphic, and an alarm summary. This ensures manageable workload and focused attention. A hardwired switch panel. The hardwired switch panel is essential for emergency and safety critical actions. It should include emergency shutdown, ESD switches, depressurization switches, maintenance override switch, MOS, enable controls, and each switch must be individually labeled, logically grouped, and laid out to reflect process hierarchy or priority. Operational override switches, OOS, are discouraged in favor of time-based logic within the IPS. MOS switches should be hardwired into the DCS console for security and availability. The actual override action may still be operated through the DCS graphic once the enable is active. Any use of these switches must be clearly indicated and recorded in the control system and shift log. Communication and CCTV panels. Each main console must include communication panel, houses telephone, radio, and intercom systems. Hands-free options such as foot-activated headsets should be considered to reduce operator distraction and improve communication speed during critical operations. CCTV panel. If used for monitoring field areas, this panel controls camera positions, zoom, wipers, and lighting. Video feeds may be integrated into the DCS display as a window or displayed on a separate dedicated monitor. Panel placement must support easy access and minimal hand movement between input devices and communication tools. This is especially important during emergency situations. FGS Mimic Panel. A dedicated Mimic panel should be included for fire and gas system FGS displays. While most alarms are presented on the DCS, FGS hardwired panels remain necessary due to regulatory and safety requirements. These can be integrated into the main console or mounted separately, but must be clearly visible and accessible during all plant conditions. Printers and video copy devices, alarm, event printers, video capture units, and logging devices should be located away from the main console area to reduce ambient noise and distraction. Shared use configurations are encouraged to minimize hardware and simplify maintenance. Alternatives such as PC-based alarm archiving or centralized servers can provide searchable logs without generating continuous paper output. Console dimensions and ergonomics. Console dimensions must support unobstructed visibility of all screens at the correct eye height, comfortable placement of hands on keyboards and pointing devices, space for documentation or writing without crowding the control area, accessibility for all users across the intended population range. Anthropometric data must be used to set dimensions, and the design should accommodate both seated and standing operation if possible. Cable management, ventilation, and lighting must also be integrated without interfering with visibility or access. Lighting considerations. Lighting design must support both screen viewing and document handling. General lighting should be adjustable, 200 to 300 lux typical, with task lights available for reading handwritten notes or detailed reports, 600 lux recommended. Light fixtures should be placed to avoid glare, reflection, and shadowing, especially on VDU screens and keyboards. Use diffusers, reflectors, or indirect lighting where possible. Avoid placing lights directly above or in front of screens. For desktop setups, adjustable display angles can help mitigate reflection. All surfaces within the operator's field of view should have moderate reflectance and neutral color tones to reduce visual fatigue. SCREEDU and display requirements. Screens used for the HMI must support high resolution, minimum 1 to 24 type 1024 or 1280 type 1024, to allow clear symbol rendering and multi-window display. Refresh rates should be 70 Hz or higher to avoid flicker. Brightness and contrast must be adjustable to suit ambient light conditions. Display bezels should be minimal to allow seamless viewing of adjacent screens. If multiple displays are tiled, they should be aligned to prevent eye strain. Touch-enabled displays must be evaluated for ergonomic reach and pressure response. Console design is a critical component of control room ergonomics and operational performance. It bridges the digital HMI with the physical workspace. A well-designed console promotes clarity, safety, and situational awareness. It enables operators to interact with the plant confidently, whether in routine operation, startup, upset, or emergency. By integrating anthropometric principles, logical layout, and interface standardization, the console becomes not just a desk, but the operator's command center. Human-Machine Interface HMI Tutorial Part 10. Part 10. A high-functioning human-machine interface, HMI, is not only a product of sound design and careful implementation, it is also the result of ongoing maintenance, integrity management, and controlled change. As the operational landscape evolves, the HMI must adapt without compromising safety, performance, or traceability. HMI maintenance encompasses software integrity, hardware upkeep, access control, and change management. These activities ensure that the interface continues to reflect the live process accurately and remains consistent with operating procedures and system architecture. Maintaining HMI integrity. The integrity of the HMI must be proactively managed by appointed personnel, typically a control systems or automation engineer authorized by the principal. This role involves maintaining the consistency, reliability, and security of both the DCS software and the HMI configuration. Best practices for HMI integrity include documenting all HMI modifications and maintaining accurate configuration records, segregating temporary and permanent modifications with clear labeling of testing or override features, following formal change control procedures for both software and hardware alterations, avoiding unnecessary software upgrades unless they deliver functional improvements or are required for security compliance, assigning a clear focal point for vendor liaison, particularly for maintenance, updates, and licensing issues, performing regular backups of configuration and graphics files, and maintaining a secure log of versions, locations, and recovery procedures, keeping security protocols, system documentation, and configuration libraries up to date and accessible. Integrity is a dynamic property. It must be preserved through discipline and visibility at every stage of system use. Software change procedure. Any modification to the HMI software, including changes to controller parameters, graphic layouts, alarm settings, or access permissions, must follow a controlled and documented procedure. This ensures traceability, approval, and validation before deployment. Key steps in the software change process include logging a change request with justification and impact analysis, reviewing the request with affected disciplines, operations, safety, engineering, testing the change in a simulation or offline environment where feasible, obtaining written approval before applying the change to the live system, applying the change during a designated window, ideally under supervision, documenting the change in system records, including version numbers and user actions, updating backups to reflect the current configuration. Temporary changes, such as disabling an alarm or altering a controller's tuning, must be labeled as such, monitored, and reverted as soon as their purpose is fulfilled. Unauthorized changes can result in misaligned displays, unsafe configurations, or loss of traceability. System security and access control. System security ensures that only authorized personnel can access or modify HMI components. This reduces the risk of accidental or malicious actions and supports auditability in regulated environments. Access levels should be configured by user role. Operator level, view and control permitted parameters, cannot alter configuration. Supervisor level, extended control functions, limited access to tuning and alarm parameters. Engineering level, full configuration access, including display editing and control logic changes. Access should be protected by passwords, physical key locks, or secure authentication mechanisms. Access logs should be maintained and periodically reviewed. Procedures must also be established for assigning, revoking, or transferring access rights as personnel change roles or responsibilities. No user should have permanent, unrestricted access unless required for ongoing system support. This reduces the risk of unintended changes and reinforces accountability. Like software, the physical components of the HMI, such as monitors, input devices, network connections, and console furniture, require routine inspection and servicing to ensure long-term usability and clarity. Hardware maintenance includes degaussing or recalibrating CRT monitors where applicable to prevent screen distortion or image retention. Replacing aging displays, especially LCD/LED screens with reduced contrast or pixel issues. Cleaning and checking the alignment of touchscreens and pointing devices. Ensuring all keyboards, switches, and function keys respond reliably. Verifying the condition of console furniture, lighting, and seating to maintain ergonomic compliance. Testing hardware indicators, e.g. LEDs, hooters, CCTV controls for reliable function. Maintaining sufficient spares and compatible replacements for critical components. Regular maintenance schedules, whether time-based or condition-based, help prevent degradation of the operator interface. A degraded interface not only slows operator response, but may also result in missed alarms, incorrect set points, or unsafe manual actions. Summary. Maintenance of the HMI is not an afterthought. It is a continuous commitment to accuracy, usability, and system integrity. Controlled software changes prevent drift from safe design. Rigorous access control ensures traceability and security. Proactive hardware maintenance preserves visibility and responsiveness. When these elements are managed together under a unified maintenance philosophy, the HMI remains a reliable, safe, and efficient interface throughout the life cycle of the plant.